So, hello everyone. Welcome to our exam prep questions on complex numbers. In our live tutorial class today, we are going to reflect on all that we learned in our previous tutorial classes where we went through the different subtopics under complex numbers. So, in this live tutorial, I'll be giving out a series of problems and I'll entreat you to pay attention to as we are solving all these problems. So my first question here is z cube. I have a polynomial z cube plus 2z squared plus ac plus b is equal to 0. If one root of this polynomial is 1 plus I, therefore find the values of a and b. So this is an application of the De Moivre's theorem, where one application is using De Moivre's theorem to find root of polynomial equations. But in our problem, we have been given the polynomial itself and we have been given one root of the polynomial. So we are supposed to find the coefficient of some terms in the polynomial. So basically, this problem that we have here is an application of polynomial equations. But here, we are dealing with complex numbers, meaning that our solution or our approach will be quite different. So let's see how this problem can be solved. So first of all, I would like to introduce you to a new theorem which you have to apply in solving polynomial problems in complex numbers. Please take note of this theorem, which you may not be familiar. So the theorem is conjugate pair theorem. So when you say conjugate pair theorem, this theorem says that if one root of an equation or a polynomial equation is z, then its conjugate is also a root. So I come again. This theorem is saying that if one root of a polynomial equation is z, then z bar, which is also the conjugate of z, is a root of that same equation. So meaning that our problem gave us 1 plus I, but we can find the second root of this equation by taking the conjugate of the 1 plus I. Therefore, we have two roots then. Meaning that whenever we are given such a problem and we are given one root, we should automatically get the second root simply by conjugating the root given. So let's see. So now let's see. At this point, let's solve what you have here. So now I know that my roots, I have one root to be equal to, let's say z1 to be equal to 1 plus I from what we're given. Then z2 will simply be 1 minus I, since the conjugate of 1 plus I is simply 1 minus I. So now we have two roots. Every polynomial equation with the degree 3 indicate that there are 3 roots. So the third root z cube, which we have no idea of, can be represented as x, right? So we don't know the third root. Now we have one root, second root, third root. And you know that if you multiply all the roots of a polynomial equation, we should get the polynomial equation back again. The focus of this problem is to determine the values of a and b. For that reason, let's try this approach to see if we are going to arrive at our answer. So therefore, let's make some references from our previous lessons we had in high school in polynomial equations. You realize that whenever you have s is equal to a as a solution for an equation, if you want to find the factor, it's simply x minus a, right? So if the solutions are x equals a and b, Then we multiply x minus a by x minus b, and that will be multiplied to give us the polynomial back. We apply the same thing here. So now if I have one root to be z1 is equal to 1 plus I, then meaning that my equation, you realize that we use we don't use x1, x2, so there's no need for the z1, z2, z3 because z is z from our polynomial. So now let's see, we are going to get z minus the expression 1 plus I as the factor of this equation, multiplying the expression z2, sorry, let me make it z. So z minus the expression 1 minus I, also multiplying this, but now let me do this first two, then afterwards we multiply it by the third factor. So multiplying these two factors, what do we get? So let's see, once I have this expression, I can break them down. So my inner expression here, I'll expand it and I'm going to get z minus 1 minus I, right? Multiplying the expression here, I'll get z minus 1 plus I, and you know clearly that I can group this here, group this also here, then I'm going to get the expression open bracket z minus 1 minus I multiplying z minus 1 in one bracket plus I. So you can clearly see that we are having the difference of squares here. So we have A, I mean here and here are the same. We have B, they are all the same. And now I have A minus B multiplying A plus B, which is the differences of two squares, right? So we are going to apply the same thing here. Hence the expression here is simply equal to z minus 1 all squared minus what? The B part is what? I squared, right? So once you get this, let's clear off what you have here. So now, once I have this expression, I'm good to go to simplify. Z minus 1 all squared will give me z squared minus 2z plus 1, right? Then minus, if you have I squared, you are going to get negative 1 in here. And this further goes on to give us 2 minus 2z. Then this is going to give me 1 minus minus 1, so plus 2, right? So now multiplying two factors of my equation, I am getting z squared minus 2z plus 2. Now, as I was saying, we simply want to multiply all the three factors. So we have 1, 2, then 3, so that we get our polynomial back again and we make the necessary equations. I mean, we compare, then we also find the necessary parameters which we want A and B. So since I have multiplied my first two factors, I only need to multiply it by my third factor, z3 equals x, which I don't know x. So let's see how we do that. So I'm going to have z squared minus 2z plus 2 multiplying the expression. I represented my last root to be z3 is equal to x, and this is just a root, so to find the factor it becomes z minus x, right? So I multiply by z minus x, and at this point z squared times z is going to give me z cubed. Z squared times negative x will give me, so let me multiply z by everything I have here. So z times negative 2z will give me negative 2z squared, right? Then z times 2 will give me plus 2z. Then I have negative x times z. I have negative xz squared. Then negative x times negative 2z will give me plus 2xz, right? Then finally negative x by 2 will give me negative 2x. At this point, I need to group and make the necessary factorization. So all powers to be at one side. I have only one z cube, so I write my z cube boldly. I have z squared here, I have z squared here. Then I'll make z squared a subject. To make z squared a subject, this is negative, this is negative. So I have minus z squared, open brackets. So let's go back to our equation and see. So our equation had the coefficient of the z squared to be what? Positive 2. For that reason, let's make the sign here positive so that when you are making equality, everything will be simpler. So let's go back to where we are. Then let me change this sign to z. Go plus. So now I have plus 2z squared. Then here z squared go here negative 2. Then this place to z squared will go here minus x. I close brackets. Then finally I move to z. I have 2z here. Then I have 2xz here. So 2z and 2xz, I'll factorize z. So plus z, open brackets, I have 2 here. Then this become plus 2x, right? Then finally, I have my term minus 2x at the far end here. And that gives me my simplification. Now let me draw my equality. So I have z cubed plus open brackets minus 2x minus x z squared plus z multiplying 2 plus 2x minus 2x all should be equal to our polynomial itself, which was given as z cubed plus 2z squared plus az then plus b is equal to 0, right? So at this point, let's see, you realize that the coefficient of z squared is what? 2 here in my actual polynomial. Then what's the coefficient of the z squared here? Is this expression. So it was actually negative 2 minus x. Sorry, so let me take this x off. So I'll have my negative 2 minus x here. So meaning that the coefficient of z squared should be equal to the coefficient of z squared by equality. So negative 2 minus x should be equal to 2 at this side, right? So at this point, I can get my x, making x the subject. When I bring x here, I'll send 2 there. So it will be negative 2 minus 2 is equal to x, giving me x of value negative 4. Now you have got to know that x, which was our third root, that was z equals x, is now going to give us z is equal to negative 4. In other way, z plus 4 is equal to 0. Meaning that our third root is a real number. A real number, or you can say a pure real complex number. That is, it has imaginary part to be 0. But our interest is not finding the value for x. Our interest is making a the subject. For that reason, let's see. Where is my a? A is the coefficient of z. What's the coefficient of z here? 2 plus 2x. Therefore, 2 plus 2x is equal to a. Is that not it? I know the value of x to be negative 4. I simply find a as what? 2 plus 2 open brackets negative 4. So I get 2. 2 times negative 4 is minus 8. Therefore, a is minus 6. As simple as that. So once I have found my a, I move to b. B is here. Then it's exactly equal to what we have here, negative 2x, right? So I'm going to have negative 2x is equal to b. Now, what is x? X is negative 4. Therefore, I'll get b is equal to negative 2 multiplied by negative 4. And that is giving me positive 8. So please, this is simply how to solve such a polynomial of complex numbers problems. you simply apply the normal polynomial rules you know, but here you remember that you are dealing with complex numbers. So the new thing learned in this problem is that we have what we call the conjugate pair theorem, which allows us to produce the second root when one is given, which simply says that if one root is given, the conjugate will be what? The second root. And that helped us to solve our problem. So without wasting more time, let's move to our second problem for this particular problem solving class. So question 2. So I have this expression here, 1 plus I to the power theta. Let me make it n. So this place is n. So our power n is what? 1000 in our problem. So meaning that we have to convert 1 plus I to the form r e I theta. To convert that, I need r, which is the modulus, giving us square root of 1 squared plus the coefficient of the imaginary, which is 1, also squared. And that is giving me square root of 1 plus 1, also equal to square root of 2. Then the theta is the argument. So for the argument, theta is simply equal to tan inverse of the coefficient of I over what? The real part. So 1 over 1. That is giving me pi on 4 radians. So meaning that we found our r, we found our theta. What's the next thing? We have to represent it here. So my 1 plus I will be replaced as square root of 2 multiplying the expression e to the power I. Then the theta is pi on 4. But in order to simplify what you have here, we need to use the extended argument plus 2 pi k, right? You close brackets, then you know that the power is already 1000. So let's come down and express what I have here. So this expression becomes square root of 2 multiplying the expression ei. If you have pi on 4 plus this, you multiply 4 by this expression, so you get pi plus 8 pi k all over 4, right? All this is to the power 1000. This is where I'm going to apply the De Morgan's theorem, which says the raw part will take the power. So I'll have square root of 2 all raised to the power 1000 in one bracket multiplying the expression ei pi plus 8 pi k all over 4. Then this 1000 will also what? Multiply what I have here, so times 1000. Then I close brackets. So at this point, what's the square root of 2 to the power 1000? You know square root of 2 is the same as 2 to the power half multiplying 1000. All this expression is multiplying here. So 4 multiply, so 4 goes into itself 1. We'll cancel 100 4 times. So I have 40 here. So e to the power I pi plus 8 pi k times what? 4. Then you add a 0, so times 40. 2 will go into itself 1 and cancel 1000. So 2 will go into 100 is of 50. So 500. So therefore my solution is simply 2 to the power 500 multiplying ei open brackets 40 pi plus 8 pi k. So if you want to find your first solution, you just put k to be what? 0. So your principal solution will be 2 to the power 500. And where k is 0, you have e to the power I multiplying 40 open bracket pi. K will be 0. and this will be your solution. So let's move to the next problem. So we have question 3. So for our third problem, let's take an expression here, I to the power 65. Then I'll have plus 1 over I all to the power 5, everything squared. Okay, so let's come back to our problem here. 4 will go into 100 25 times. Then you add a third zero to it. You have 3 zeros, so you just take the first two first. So 4 will go into 100 of 25. Then you add a 0 to it, so you get 250. So this place becomes 250, right? 250. So meaning that I'll have 250 here. Once again, that was an error. Then 250, right? So that was a slight mistake we made. And please take your calculator and be punching alongside as we solve to confirm our simplification. So back to what we're doing here. Our third question here is I to the power 65 plus 1 over I to the power 5 all squared. So this is also the complex operator problem. How do we go about it? You use the basic powers. So we have I squared giving negative 1, I to the power 4 giving 1, I to the power cube giving negative I. And with this, you should be able to break this down and simplify. So if you have 65, normally when you are dealing with high powers, it's advisable to use the I to the power 4 to make the simplification easier. So what is 65? So if you want to express 65 in terms of 4 will go into 65 how many times? So you divide 65 out of 4. So you realize that 4 times 16 will simply give us 64, right? So meaning that we can express our I to the power 65 as I to the power 4 all to the power 16, because this time this will give us 64, but there will be a remaining 1 to make it 65, and that will still be I. So when we simplify this back again, or when you multiply it back again, you'll be getting I to the power 64 times I, which is I to the power 65, getting what you have here back. So we are only modifying this, but we are not doing anything to it. So plus, this is to the power 5. So I'll have 1 to the power 5, which is 1 over I to the power 5. And everything here is squared. So this will be, if you have I to the power 4, you know the answer is 1. So you simply get 1 to the power 16 multiplying I plus, then this is also 5. You can make it 1 over I to the power 4 multiplying I, right? All squared. 1 to the power 16 is 1 times I plus, this is also 1. So I get 1 over I, everything squared. So we can clearly make this as I plus 1 over I all squared, right? So when you multiply what I have inside here, remember that 1 over I itself is equal to negative I. Why? 1 over I. You use the conjugate. So you get I times I is I squared, which is negative 1. So this is equal to negative I. I will simply make my substitution I. Then this will give me negative I all squared. So I minus I is all 0 all squared, and our answer is simply 0. Now let's go to our fourth question here. So question 4. So for question 4, let's see this expression here. Z is equal to I to the power negative 2i. So we have to simplify. We have to simplify the expression Z is equal to I to the power negative 2i. How do we simplify this expression? Once you have a complex number to the power a complex number, we apply natural log, that is logarithm of complex number. Natural log to bring the power down. So at this point, to solve this problem, we simply find natural log length of Z is equal to length of the expression I to the power negative 2i. So I'll have length Z is equal to length of this expression. By the properties of logarithm, my power will come down as negative 2i length of I, as simple like this. So at this point, I'll have length Z is equal to negative 2i, but at this point, our length I here, we have to simplify. Whenever you are dealing with logarithm of complex number and you are using natural log, simply convert our complex number to the polar form for easier simplification. So our I in the polar form, this is a unity complex number. So meaning our R is 1, that is the modulus is 1. So you simply get e to the power I, then the theta. On the Argand diagram, I falls here, so 1. So having 1 on the imaginary plane is what we call I. And its argument is simply 90 from the x plane. So this is 90. So we simply get pi on 2. But we have to apply the extended argument 2 pi k. So once I have this expression, I can simply substitute what my I with this whole expression. So my length Z is equal to negative 2i length of the expression e to the power I pi on 2 plus 2 pi k. Now what the rule is saying is that if you have natural log of e, then everything here will be 1, leaving the answer to be our power. I say length of e to any power a is simply equal to a by the properties of logarithm. So at this point, we simply have length Z to be equal to negative 2i multiplying I pi on 2 plus 2 pi k. So at this point, we don't want length Z. The question asked us to simplify Z is equal to. So we have to remove the length here by taking E length Z, E the whole expression here, negative 2i I pi on 2 plus 2 pi k. E to the power length Z, as we did from this side, is simply equal to Z, right? So Z will then be equal to this whole expression, e to the power. Now at this point, we have to multiply everything I have here. Negative 2i times I, what's the answer? You know that I times I is I squared, also as negative 1. So I'll get positive 2. I'll write my positive 2 here. Then I'll get pi on 2 plus 2 pi k. So at this point, I can still expand it further and I'll get Z to be equal to e to the power pi plus 4 pi k. And this simply gives our solution of our logarithm of complex numbers. It's so simple. So let's move to our next question. So what's the question number for this? This was the question 4. So let's go to question 5. So question 5. So to solve question 5, I have this expression here. 1 over x plus iy plus 1 over 1 plus 2i is equal to 1. Find x and y. So you can clearly see this is an algebraic of complex numbers. We are just manipulating the division, the multiplications, and everything. So I have 1 over x plus iy plus 1 over 2i, 1 plus 2i is equal to 1. And we've been asked to find x and y, right? So to do this is simply by making what you have here the subject. 1 out of x plus iy is equal to 1 minus 1 over 1 plus 2i. So at this point, I'll get 1 over x plus iy to be equal to, you have to simplify this. In algebraic expression, you just cross multiply. I'll have 1 plus 2i. So this one is 1, so I was actually subtracting. So this is the subtraction sign. So 1. So okay, so before that, let's see something here. We have two ways of treating this question. It's either we conjugate this, we simplify this expression here before we go on with our subtraction. So let's try that one. So minus the expression. So 1 over x plus y is equal to 1 minus the expression 1 over 2. 2i plus 1, let's make it that way, times 2. So times 1 minus 2i, that's the conjugate over 1 minus 2i. So at this point, see what you are going to do. I have 1 over x plus iy to be equal to 1 minus the expression. So this expression here, I'm going to, there is minus sign here. Multiply the top, which is 1 minus 2i all over. When you multiply this and this, we have 1 plus 2i multiplying 1 minus 2i. Remember that this is differences of 2 squared. So you get 1 squared minus 2i all squared. As simply like that. So this gives us 1 minus the expression 1 minus 2i over 1 squared minus 2i all squared is what? 2 squared is 4. I squared is negative 1, right? So I'll get 1 minus negative 4, right? Hence 1 over x plus iy is equal to 1 minus the expression 1 minus 2i all over 5, because 1 minus minus 4 is 5. And this is simply equal to 5 times 1 is what? 5. Is that not it? Minus 1 minus 2i all over 5. So 1 over x plus iy is simply equal to, when I open this bracket, I'll get 5 minus 1 plus 2i over 5. This is equal to 1 over x plus iy is equal to 5 minus 1 is 4 plus 2i over 5, giving me 4 on 5. So let me make it decimals and see. I'll simply get 0.8. 2 over 5 is the same as 0.4 plus 0.4i. That is 1 over x plus y, right? So I'm going to get 1 over x plus iy to be equal to 0.8 plus 0.4i. I'll make this a subject and I'll get 1 over the expression 0.8 plus 0.4i to be equal to x plus iy. Meaning I need to still simplify this expression here before I can equate it towards this. Is that not it? So let's see. So how do I simplify 1 over the expression 0.8 plus 0.4i? I simply do that by finding the conjugate minus 0.4i all over 0.8 minus 0.4i. This simply gives 0.8 minus 0.4i all over. This times this, I'll get 0.8 squared. This times this, I'll get minus 0.4 all squared equals x plus iy. So I still go on simplifying. So 0.8 minus 0.4i all over 0.8 all squared is what? Remember 0.8 was equal to 4 over 5. So I can make it what? 16 over 25 minus 0.4 is the same as 2 over 5. So I can get, here I is there, please. So I squared is negative 1. So I'll get plus 0.4 is 4 over 25. So this sums to give me 0.8 minus 0.4i all over 20 on 25. So now for me to show clearly the simplification, I only need to break down what I have here. So I'll have 0.8 is the same as 4 over 5 all over 20 over 25 minus 2 over 5i all over 20 over 25 should give me x plus iy. So this is 4 on 5 times 25 over 20. 5 goes into itself 1, go here 5. 4 go here 1 and go here 5. Is that not it? So 5 and 5 will cancel to give us 1. So I'm simply going to get 1 minus. This side I'll simply get 2 on 5 times 25 on 20. 5 goes into itself 1 and go here 5. 2 go into itself 1, go into 20, 10. This is half. So half I equals x plus iy. So at this point, my x is simply equal to 1, as you can clearly see. Then y is simply equal to negative half. And that gives us the solution for our fifth question. So let's see the next question we have. I simply have this expression z cubed minus 125 is equal to 0. That is question 6, right? So for this question, z cubed minus 125 equals 0. To simplify this, we know that basically you just find z cubed equals 125. Then we take the third root on both sides. Is that not it? Giving you z is equal to 5. But as you've seen, z is complex number. So in complex numbers, we don't do this simplification. No. Once you see z cubed, this is an equation having 3 roots: z1, z2, z3. How do we get each root of the equation? Always the first thing to do is make z the subject. So z cubed equals 125. And at this point, our z is equal to 125 all to the power 1 out of 3. As simple as that. At this point, you realize that 125 here, before we can apply the Morvis theorem to find the roots z1, z2, z3, the first thing we need to do is to convert 125 into a polar form. This is a pure row number, but on the diagram diagram, we can represent 125 on our positive real number axis. So let's say 125 here, and realize that it will have an argument of 0 since it is parallel to the x-axis, and its magnitude will simply be the 125. So I'll get 125 e to the power I, then the theta is 0 plus 2 pi k, which is the extended argument. All this expression is to the power 1 out of 3. So at this point, this gives me 125 e to the power I multiplying 2 pi k to the power 1 out of 3. So you get our root z1 when k equals 0, z2 when k is equal to 1, z3 when k is equal to 2. Is that not it? So let's see. Right now I'll get 125 to the power 1 out of 3 multiplying e to the power I 2 pi k all on 3. At this point, this gives me 5. So I'll get 5 e to the power I 2 pi k on 3. So z1 when k is equal to 0 is simply equal to 5 multiplying the expression e to the power I 0. If here is 0, everything here will be 0. So I'll get everything here to be 0. E to the power 0 will give me 1. And this will simply be 5 times 1 equals 5. So the first root of the equation is simply 5. Then the second root z2 is equal to when k is equal to 1. And we'll get 5 multiplying e to the expression I 2 pi, then k is 1. Everything on 3. So this gives me 5. Then e, so here will give me 2 pi on 3i. And that gives me my second solution. So you can expand this for this to become for this to become 5 open brackets cosine of 2 pi on 3 plus sine of what? 2 pi on 3. And that gives us our z2. Then finally our third root is when k is equal to 2. So when k is equal to 2, we simply get 5 multiplying the expression e to the power I 2 pi times 2, which is the value of k, all over 3, which is equal to 5 multiplying e to the power 4 pi on 3i. So at this point, I'll simply have my third root z3 to be equal to 5, then cosine of 4 pi on 3 plus I sine of 4 pi on 3. And that gives us a solution for our equation. So that's the end of our sixth question. So take notes, do the calculation as I also solve so that you don't get lost. So let's see our question 7. So our 7th question, let's see the question we are going to solve. So I have this expression here, 1 minus I over the expression 1 plus I. All this to the power 100. So what this problem is that we are to simplify what you have here, a complex number over another complex number, all to the power 100. We can refer from properties of complex numbers that if you have two complex numbers, r1 e to the power I theta 1 over r2 e to the power I theta 2, all these to the power n, then the properties of polar form will say that this is the same as r1 over r2 all to the power n, then ei open bracket theta 1 minus theta 2 all multiplying n. Is that not it? So this is what we are going to follow to solve the problem we have here. So you can actually see that I'm to convert this to polar form, this to polar form. So 1 minus I in polar form, what are you going to get? R will be equal to square root of 1 squared plus plus negative 1 all squared, and that will give us square root of 2. Theta, so this R1, theta 1 is equal to tan inverse of negative 1 on 1. That is simply giving us negative pi on 4. Remember, we did principal arguments and also the two conventions. I'm using the conventions negative pi to pi. So I'm going to take the negative value of this as my principal value, then plus 2 pi k. So the expression then becomes square root of 2 e to the power I open brackets negative pi on 4 plus 2 pi k. Right, so that's for the first one. Then 1 plus I'll have my r2 simply also equal to square root of 2 since they will have the same coefficient. But theta 2 is tan inverse of 1 on 1. That is giving me pi on 4 plus 2 pi k. So my complex number in polar form becomes square root of 2 multiplying pi on 4 plus 2 pi k. So sorry. So square root of 2 multiplying I pi on 4 plus 2 pi k. Then we have to replace them. So I have my expression with numerator square root of 2 e to the power I open brackets negative pi on 4 plus 2 pi k all over root of 2 e to the power I over pi on 4 plus 2 pi k. All this to the power 100. Root 2 will cancel root 2. Then at this point, as I told you, our argument will subtract. So I'll have ei open brackets negative pi on 4 plus 2 pi k minus the expression I pi on 4 plus 2 pi k, and everything here is to the power 100. So at this point I want to just subtract my powers here. So I'll have I open brackets this, which is negative pi on 4 plus 2 pi k. Then here I'll have negative pi on 4 minus 2 pi k, everything to the power 100. So at this point this will cancel this, and this gives me negative pi on 2 because I have negative 2 pi on 4. So this is simply equal to e to the power I negative pi on 2 all to the power of 100, and this is equal to 100 will multiply this and it will give me 50 e to the power negative 50i. So pi is already there, so e to the power negative pi 50i, and that is simply the solution for our expression. You can simply convert this into your linear form since the problem was given in linear form. So you simply get cosine of 50 pi plus I sine 50 pi. Since it's minus, let's put minus here. So minus I sine 50 pi. And that is the solution for what the problem put forward. So at this point we have touched on, let's have a recap. We have touched on De Moivre's theorem application, De Moivre's theorem application. Then we have done several polar form representation. So you can see that in complex numbers the polar form is of a greater relevance since most of the computations you require a complex number to be in polar form. We have also done logarithm of complex numbers. Right, then we have also done the algebraic computations, so that is multiplications and all that for complex numbers, as well as the nth root, which are all falling under the De Moivre's theorem. So apparently we've touched on almost everything under complex numbers. So at this point let me try giving you a problem for you to try your hands on. So try this question, I to the power I. Simplify this expression here, I to the power I, and let's see. So I'm breaking for short time so you can test your hands on how to simplify I to the power I, so that when you all solve it you compare it to your actual answer. So without wasting time we come back. Then if you have I to the power I, to simplify we can simply say z is equal to I to the power I, And at this point, we take lane on both sides. So once we take lane on both sides, I'll have lane Z to be equal to I lane I. And please take note, capital lane and small lane are not the same. Whenever you see capital lane, you are expected to put in your extended argument. So for capital N is extended, then the smaller n lane is your principal argument. So I'll take capital lane on both sides, and at this point, my lane I, expressing I to polar form, I hope by now you have it in mind. So I pi on 2 plus 2 pi k. I'm adding the 2 pi k because I took the capital lane, so I have to bring the extended argument. So you have I multiplying lane of EI pi on 2 plus 2 pi k. So lane Z, and at this point lane Z is simply equal to I multiplying the expression. This and this will bring the top down, I pi on 2 plus 2 pi k. So this is equal to, you have to take Z because we made Z to be there, so we need to bring the Z back by making e to the power lane Z is equal to e to the power I multiplying pi on 2 plus 2 pi k. So this gives us Z. Then this gives us our I pi on 2 plus 2 pi k. So our complex number becomes negative pi on 2 plus 2 pi k, which is also equal to negative pi on 2 minus 2 pi k. And this is the solution for the expression I to the power I. So at this point, I would like to end, since you've touched on every part of complex numbers. And mind you, for the addition, subtraction, you are only going to apply them in solving problems. You wouldn't be given a question to add two complex numbers. That is too basic. So all these problems I've taken you through comprises all the necessary arithmetics as well as the necessary principles. That is the De Moivre's theorem, the conjugate pair theorem, and the others. For you to solve every complex number problem, you should get to know your basis, that is the real parts of a complex number. You should get to know your imaginary parts. Then you should get to know how to represent complex numbers on the Argand diagram. So let's try the last question on how to represent complex numbers on an Argand diagram. So if I give you, let's say 2 minus 3i to represent on the Argand diagram, you know the Argand diagram has the imaginary axis on the y, then the real part here. So here is negative im, here is negative re. 2 is positive, so to 4 here on the row. Negative 3i, so you have 3 on the down here. So our complex number will have here z2 minus 3i. Then you draw a line from the origin to touch it. So this is a simple representation of complex number. The angle here is what you call the argument. And the distance from this side, origin to this point, is what we call the modulus. So these are all the basic stuffs, and I'm trying to give you an overview of the complex number system. So at this point, we can call whatever we are doing off, because we are done with complex numbers and we solve several examples, and this example should help or equip you with your exams in complex number system. Thank you for joining me in this live tutorial class, and hoping to see you in all the subsequent live tutorial classes in matrices, vectors, and the others.